In this electrical circuit problem, I have a single loop of wire, and I want to find the transfer function that's going to take me from some input voltage, EI, to my output voltage, EO. Now, really what the output voltage is the measurement of the voltage across the capacitor. You'll notice that how I'm measuring EO is this open wire. It's not a closed loop to the right of C. We can think of it as if we had a multimeter and we were measuring the voltage across the capacitor, what would it be reading? That's what E out is. This is not two loops of wire, which we will see in another example. So I want to find my transfer function. G equals E out over E in. And again, I'm going to make my own diagram, even though it's going to look largely the same, but that way I'm able to mark it up for when I want to use like KVL to derive some of my equations. So more or less it will look exactly the same. I am going to just add a dashed line here to indicate that that is my EI, my input voltage. That's going to go across this inductor with inductance L and a resistor with resistance R, and then come across this capacitor with capacitance C. And what I'm trying to measure here, I'll put a dashed line there, is E out, which is the voltage across the capacitor. And we're given to use this clockwise current I. I again will stick with that because that's what was given, but I could have decided to do counterclockwise as well. So that is my diagram. I'll just clean up the bottom here a little bit so that everything is connected. All right, so I will mark this lower point as A. I'll add a B, a C, and a D here, which will just be for discussion purposes as I'm doing my KVL equation. It's a single loop of wire that closes back in on itself, so KVL is going to be the strategy I'm going to use to derive at least one of my equations. We'll see how many equations we actually need for this problem. Now, so like I said, I'm going to start with a KVL. So I'm going to sum my voltage as I go from A back on itself. And KVL says that that net voltage has to be 0. Right, so as long as I go in a closed loop, I can make this equation. For simplicity, I am going to go with the direction of current as I've established it. So clockwise is the direction I will travel. So first I will go from A to B. I'm going to go across my voltage source or my voltage input, capital E sub I. Remember, we are working already in the Laplace frequency domain, so everything will be capitalized now. So I have a voltage gain as I go from A to B. We're going to assume that positive EI will be from A to B, and a negative EI would go B to A. Now it's an input voltage. It could be positive or negative. It can change over time. This will be our assumption of direction here for input voltages. Next, I'm going to go from B to C. I am going with the direction of current. Therefore, there is a voltage drop across my element. The voltage drop across the inductor is going to be LS times the current, which in this case is capital I. Now I've arrived at C. From C to D, I go over one element. It's a resistor. So minus the resistance R times the current through the resistor, which is I. I've arrived at D. Now I can return to A by going across the capacitor and then going through the wire back to A. So there's going to be a voltage drop because once again, I'm going with the direction of current. So minus, this will be 1 over C times S times the current going through the capacitor, which is I. And that takes me back to A. Notice in this one, I only have this one loop of current. That E out is just that measurement. It's not another loop of wire. We will see that in a following example where we have multiple loops of wire and we'll have multiple currents. This is not that kind of case. So we have this one equation already in the Laplace frequency domain. Let's see where we are, if we need to add more, if we have enough. Looking at the equation we just made, we have our input is E sub I, and we have an output of, well, the current in this loop I. L, R, C are constant, S will not count here. So we do have one equation, one unknown. However, if we go back up to what we need to find, I want E out, the voltage across the capacitor, over my input voltage EI. So I actually do need at least one more equation because E out is not yet an output that I have listed. So second equation, I need to know an equation that has E out in it. So one thing I can do is I can see the path from D to A. There are two paths I can take to get from D to A. One, I can go through the capacitor, or I can go through E out. But I know that if I go from D to A, the voltage drop has to be the same no matter what path I take to get there. So I can write, let's say I go through the capacitor, the voltage drop is going to be that negative 1 over CS times I. And if I take the alternate path, going through E out, I will get a negative E O. Because again, I will be going opposite of the direction of its polarity. I'll be going from its positive to its negative end. Again, it would depend how I define it. That's how I'm going to define it here, that it would also be set up in this sort of manner. All right, so that's my second equation, and I have a negative and a negative, so I can just get rid of those negative signs, or that's by multiplying through by -1. I can write equation 2 a little bit more simply. In equation 2, I've added an output, EO. So I have two outputs, but now I also have two equations. This is going to be solvable to get me to the transfer function that I desire. And I'm going to let Mathematica do that work for us. Now I'll transcribe my equations into Mathematica. I'll call the first one KVL. So this is going to be, well, 0 equals EI minus L times S times I. Now, one thing to note, you'll notice that capital I is black, it's not blue, because Mathematica treats capital I as the square root of -1. So for the purposes of Mathematica, I'll just call it I1 so that it thinks it's a variable and not a constant that it already knows. I just have to remember to do that everywhere. So minus R times, again, I1 for the purposes of Mathematica, minus, and I'll make it look nice here, 1 over C times S. And you'll also notice here, C is black because Mathematica will think that C is the speed of light. It has a built-in constant for that. So in Mathematica, I actually need to change that to lowercase c, or that would be one way to compensate for it, times the I1. All right, so unfortunately, two things we have to worry about. We don't want to use capital I, and we don't want to use capital C. So remember, in the basic syntax of Mathematica, capital letters or capitalized things can be built in functions, or in this case, constants, that we just have to be aware of. So I just had to rewrite it so that now it's appearing in blue. It's treating it like an unknown variable. So that is my KVL equation, and everything looks normal with it. And then I have, well, I'll just call it EQ2. It's coming from just the voltage drop between A and D, or D and A in this case, being the same no matter which path I take. And putting this together, this is going to be 1 over C times S times that I1, I'm calling it, equals EO. All right, we already checked, and we have these two equations, and we have two outputs. So we're going to be able to solve for our two outputs. So solve our KVL equation with our voltage drop, which I'm just going to call EQ2. And the outputs here are I1, again, for the purposes of Mathematica, and E out. All right, solving that, and I'll again simplify this a little bit. I get my two, what could become my two transfer functions. I have one for the current in my loop, which I was not asked to find in this example, but it's here. And then I have my other transfer function for E out. So I will save this right-hand side. It's pretty straightforward. I don't need to necessarily go through all this extra work. It's already in the form basically in the form I want. But the transfer function is EO over EI. It's E out over EI, so I divide both sides by EI. So I'm actually left with 1 in the transfer function. And really, this is already in a fine form. I have an S squared, I have an S, I have a constant. I really don't need to go through the extra effort to do the collection or anything like that. This is ready to put back into my handwriting and then finalize at this point. I'm just going to recopy this. I called it G up top, but again, that was E out over EI as my transfer function. So the voltage across the capacitor over the input voltage. And I'll just recopy this in my standard form. So I will have CLS squared plus CRS plus 1 in my denominator. And that will be then the final transfer function that I was looking for in this problem. To recap the steps that we took to get to this transfer function, we were given this loop, this single loop of wire in our circuit, and we are looking for the output being the voltage across the capacitor. So just one loop makes up this problem. So I recopied this fairly simple diagram to one I can mark up, and I just put dashed lines here across these openings of where my input voltage is going to be, and then my output, or the voltage that I am reading. I used in this single loop a KVL equation where I started at A, I went with the direction of the current that I assigned, so clockwise, and ended up back at A. So I had an increase in voltage across EI, a voltage drop across the inductor L, a voltage drop across the resistor R, a voltage drop across the capacitor C, and I was back at A. So that had to sum to 0. So that was my first equation. That had one output, the current, and one input, E sub I. However, I need to find my transfer function of E out over EI. So that necessitated a second equation. Here, I noted that if I go from D to A, there's two paths I can take, but the voltage drop must be the same along any of those paths. So to go from D to A, I have that voltage drop across C, which I had already noted up here, but I know that this was originally a negative 1 over CS I. Or to go from D to A, I can go across EO. So I had the voltage drop across EO as I was going from top to bottom, so I had a negative EO. Those two negatives canceled, and I was able to write it as this positive. Now I added another output, EO, to my list. So I have two equations. One of my outputs is my desired output for my final transfer function. I have my input, so this became a solvable system. I put it into Mathematica, and I was able to get at least the makings of transfer functions for I and E out. I only was interested in E out for this example, so I rearranged it and put it into the standard form with descending powers of S in the numerator and the denominator to get my final transfer function for this problem.